So let's get started. We are going to continue what we have discussed last time. We'll learn how to develop the stress-strain diagram. And here we have a typical stress-strain diagram for different materials. Here we have the glass, steel, aluminum, concrete, and soft rubber. It's very important to know the elastic behavior. Sometimes, or in most cases, those material here is going to show elastic behavior. So elastic behavior, it's mean that when we are going to develop the stress-strain diagram, let's say that the loading process at that point. So then I'm going to release the force here. So if I'm going to release the force, that means the value of the strain and the stress is going to decrease. And if that line here get back to the original here, it means that the material exhibits elastic behavior. So here, in order to, of course, to get the stress-strain diagram, I need to apply a force for this specimen. And of course, when I'm going to apply a force, then I'm going to have delta L. Delta L, I'm going to convert delta L into the strain. So the curve is going to increase. It's going to be like that. What if I release that force? If I'm going to release that force, that means the value of the stress is going to decrease, and also the value of the strain is going to decrease. But sometimes this line here is not going to get to the original point. In that case, that means I have permanent deformation. But if I manage to get to the original point here, that means I have elastic behavior. So here, if I apply a force, then I'm going to have increase in the length. If I release the force, if that delta L became or return to the original like this one here, that means the material showed plastic behavior. Also, we have linear and non-linear behavior. Again, if I have a specimen, if I'm going to a specimen of any material, if I'm going to have stress-strain diagram in a form of a straight line like that, we are going to say that we have linear behavior. Okay, if the stress-strain diagram look like a curve like that, we are going to say that we have non-linear behavior. Okay, and we don't need to mix up the linear and non-linear behavior with elasticity and inelasticity. Okay, so for example, here I have linear behavior for that material because here I have a straight line, and also if I release the force, then the line here is going to get to the original point here. It's mean that I have linear behavior and elastic behavior. The other case, which is here I have the stress-strain diagram for a material here. Then I apply a force, and as a result, a curve is generated between the stress and the strain. And if I'm going to release the load at that point, then the curve is going to get back to its original point. In that case, I have non-linear, but it's elastic. But if I get to that point here, and I'm going to release the force at that point, and the curve did not return to the original point, that means I have non-linear behavior and it's inelastic. So if I have a linear material, that means it has a straight line. If I'm going to have an elastic material, that means the material is going to return to its original shape after I release the force. So linearity and elasticity should not be confused. We should not mix the linearity and elasticity. Okay, so a linear materials stress-strain relation follow follows a straight line. An elastic material returns to original shape when the load is removed or released and react instantaneously to changes in load. Also, we have properties of elastic material. If the material is elastic, then we have a certain properties that we can determine. The first one, we have the modulus of elasticity, or Young's modulus. So here we learn how to generate the stress-strain diagram. Okay, so in case that I have linearity, if the material shows linearity like this one, then the modulus of elasticity is the slope of that line. Of course, the slope, it's mean that I have the rise over the run at any point of the line here. So the slope of that straight line represent the modulus of elasticity. So if the value of the slope is high, that means that material is going to show a small deformation. If the value of the slope is low, that means that material is going to show large deformation. So the modulus of elasticity can show us how the material is going to resist the deformation. Also, we have the Poisson's ratio. Poisson's ratio. If I'm going to have material like this one here, if I'm going to apply a force for that material, let's say tension force, then the length here is going to increase, right? So here we have the original lengths, and here we have the final lengths. So the lengths here increased, right? But look at the lateral dimension here. This dimension, it was originally like that, and when we apply the load, what would happen? What happened to that dimension? It decreased. So if I apply a tension, the axial dimension, this one here, is going to increase, while the lateral dimension here is going to decrease. So the ratio between the lateral strain, this one, and the axial strain, we call this Poisson's ratio. And here we put minus, because if this dimension is going to increase, this one is going to decrease. So this one is going to be minus. So minus and minus is going to be positive. We put minus here to make sure that the value of the Poisson ratio is always positive. Let's say that I have compression, not tension. If I'm going to have compression, if I'm going to apply compression to this sample, that means the axial dimension, this one, is going to decrease, while the lateral dimension is going to increase. In this case, this one here is going to be minus, and this one is going to be positive. So minus is going to cancel the minus here, and again, the value of the Poisson ratio is going to be positive. Okay, so it doesn't really matter if it's if we are going to apply tension or compression. The value of the Poisson ratio here is going to be positive. And the range of the value of the Poisson ratio is from 0 to 0.5. That means the maximum value for the lateral strain is going to be half of the axial strain. Okay, but in practical, the value is from 0.1 to 0.45. So in practice, the maximum value is 0.45. So it's very important to understand the nature of these properties, the modulus of elasticity and the Poisson's ratio. And I know that because in order to take this course, you need to pass strength of material. You deal with the value of E and the value of Poisson ratio a lot, but you may not truly understand what they really mean. Here we say that if the curve is a straight line, the slope of that curve represents the modulus of elasticity. But like you can see here, some material does not show a straight line in the beginning. So in this case, what should I do? So sometimes the response is not linear, like you can see here. And we said that in order to determine the modulus of elasticity, we need to determine the slope of the straight line. But here we don't have a straight line. So in this case, they proposed 4 types of modulus of elasticity. We have the initial tangent modulus. I'm going to draw tangent to the original point here, and then I'm going to determine the slope of that line. We call this initial tangent modulus. And also we propose another type of modulus of elasticity, the secant modulus. In this case, I'm going to determine a point on the curve, and I'm going to connect that point with the origin point. I'm going to draw a line between those points, and then I'm going to determine the slope of that line. We call this secant modulus. Also, we have the chord modulus. I'm going to determine 2 points on that curve, and I'm going to draw a straight line, and then I'm going to determine the slope of that straight line. And the last one, I'm going to determine a point on that curve, and I'm going to draw a tangent to that point, and then the slope of that line is going to be the tangent modulus. So I have 4 types of modulus of elasticity. I have the initial tangent modulus, I have the tangent modulus, I have the secant modulus, and I have chord modulus. So how I'm going to determine those points and this point and that point? So that is going to determine, or that is going to depend on the stress or the strain level at which the material typically is used. So in order to determine which modulus of elasticity should be used, we need to understand the stress or the strain level at which the material typically is used. Just here we have a general idea about the different types of modulus of elasticity in case the relation here is not linear. Here we have typical modulus and Poisson's ratio for different materials. We have aluminum, brick, concrete, steel, and wood. Here we are going to find out that the largest value for modulus of elasticity here in steel. So steel, it has the largest modulus of elasticity. That means the resistance to deformation in the steel is very large compared to other materials. And also here we have the Poisson ratio. It gives us how the lateral strain is going to take place compared to the axial strain. Also, we need to talk about the elastoplastic behavior. Not all the material is going to show us only elastic behavior. Most of the material is going to show elastic behavior in the first part here, and then they are going to show plastic behavior on that part. So it's very important to understand the elastoplastic behavior. So we have a point that it's transition point between the elastic behavior and the plastic behavior. We call this elastic limit. So this point is going to differentiate between the elastic behavior and the plastic behavior. Within this region here, if you are going to release the load at a point within this region, the material is going to get back to its original shape. While if you release the load within this region here, the material is not going to get to the original shape. That means you are going to have permanent deformation. So in elastic behavior, that means the deformation is recoverable, okay? But in the plastic deformation, we are going to have permanent deformation. Okay, so let's see how this is going to work. In order to generate the stress strain diagram, of course, I'm going to apply a force for a specimen for that material. And as a result, I'm going to generate the stress strain diagram. In this case, I tested the material until the failure. So here is the failure point. So the force is applied, resulting in stress and stress diagram. We got to that point here. Okay, so at that point, the value from here to here is the total strain. So at that point, I have deformation. I have strain with that value. Then at that point, what if I release or remove the force at that point? So what will happen? We know that since the point is after the elastic limit, that means the behavior is going to be plastic. That means the material is not going to get to its original shape. But what will happen? What actually happen? I'm going to have a straight line parallel to the initial slope. So the material is going to get back, so that the line here is going to be parallel to the original line. So I'm going to have something like that. So that line here is parallel to that line there. Okay. So that means part of the strain is going to be recovered. That means this part was elastic, while this part was plastic. So I only managed to get or to recover the deformation within this region, while this part here it was a plastic strain. Then what if I apply a force again to that material? Then it's going to follow this path. It's going to go like that, and here is going to have the new elastic limit. So the elastic limit is going to be shifted to that point. So now this point here is the point between the elastic behavior and the plastic behavior. So if I'm going to apply the force here and I'm going to remove that force, the material is going to get back to the original shape. Okay, and the process is going to repeat itself. So if I'm going to apply the force, then here I have the new elastic limit. If I get to that point, and then if I'm going to remove the force, then also I'm going to have plastic behavior, and I'm going to have a line parallel to this line and that line. So it's very important to understand the elastoplastic behavior as well. Sometimes the elastic limit is not clear. So you are going to ask me, how did you know the elastic limit for that material? So like you can see here, I have a stress strain diagram for some material here. Then I need to know where is the elastic limit. The elastic limit differentiate between the elastic and the plastic behavior. I have two methods in order to do that. The first method, we call this the offset method. In the offset method, we are going to draw a line like that. Start from 0.2% of the strain, and that line is going to be parallel to the initial straight line here. And the intersection here is going to represent the transition point or the elastic limit. So in this part, I have elastic behavior, and in this part, I'm going to have plastic behavior. I have another method, which is the extension method. In that method, I'm going to draw a straight line at 0.5% of the strain, and the intersection here represent the transition point or the elastic limit. So from here to here, we have elastic behavior, and after that point, we are going to have plastic behavior. So if the elastic limit is not clear, you can use either the offset method or the extension method. Here we have a typical stress strain behavior of mild steel. So here we put a specimen of steel and we apply a force until failure in order to generate the relation between stress and the strain diagram. So initially within that region, the material was like that. When we apply the force, we are going to have increase in the strain. And this point here is the proportional limit. The proportional limit is the transition between linear and non-linear behavior. So the behavior here before that point, it's linear behavior. And after that point, we are going to have non-linear behavior. And here we have the yield point. The yield point is the elastic limit. Here, the transition between the elastic behavior and the plastic behavior. And we are going to call this yielding. So in the yielding process, here, the yielding process, we are going to have large strain with a little bit stress. So with increasing a little bit stress, we are going to have large strain, not like this region. In this region, we need to apply large stress in order to get small strain here. But at that region with a little bit stress, we are going to have large strain. We call this yielding. And the maximum stress here, the maximum stress on the curve, we call this ultimate strength. And the final point before the failure here, we are going to call this rupture. And the point from here to here, we are going to develop what's so-called necking. The material is going to develop a neck. Okay. So here you can see the changes or the deformation that is going to take place in a specimen of steel. So we need to understand those terminology, the proportional limit, we discuss all of this here, and the elastic limit or the yield point, the yielding, and the ultimate stress, the rupture stress, and we need to understand the difference between the brittle material and ductile material. If I'm going to have brittle material, that means I have a little plastic deformation before the failure, like the glass and the concrete. Typically something like that. That means I'm not going to have yielding. While material like that, I'm going to have yielding. That means this material is ductile material. That means I'm going to have a lot of plastic deformation before the failure. So obviously, in the case of steel, I'm going to have ductile material. That means before the failure, I'm going to have a lot of plastic behavior. So this terminologies is very important for you to understand. Also, we have the work and energy. Since the work is force times distance, we know that if I multiply the force times the distance, I'm going to get the work or the energy. And if I'm going to have a specimen, if I'm going to apply a force for a specimen, I can generate the force displacement curve, and the area under the curve is going to represent the work or the energy, like you just learned in dynamics. Here, the stress strain diagram represent the force displacement diagram. So the area under the curve is going to represent the work, but it's going to be the work per unit volume of the material. So the area under the curve here represent the energy or the work that has been done on the specimen or on a certain material. But this one is going to be work per unit volume. We have two types of work or energy. We have the modulus of resilience. This one is going to be the energy required to reach to the yield point. Remember the yield point, the transition point between the elastic and the plastic. So if I'm going to draw or determine the area under the curve up to that point, this represents the modulus of elasticity. We have the other type, which is a toughness. This one represents the energy required to fracture. So here we have the fracture point, and if I'm going to determine the area under the curve here, we are going to call this the toughness. So we have the modulus of resilience and we have the toughness. The modulus of resilience is the energy required to reach the yield point, while the toughness is the energy required to fracture. Sometimes you may think that if the material is strong, that means the energy is going to be large as well. So here we have a stress strain diagram for a material with high strength and a material with lower strength. So for this material here, it has larger strength than that material there. But if you are going to determine the energy or the work, it's obviously that the energy for the lower strength here, strength material here, is going to have the higher toughness. So it's not always if the material it has a higher strength, it's mean that it's going to have a higher toughness. So here for your homework, you are going to have a problem similar to this one here. So here we have a specimen and we apply a force for that specimen up to failure. And as a result, we generated a stress strain diagram. Here we have the stress and here we have the strain. Here it's required to determine a certain properties. First, we need to determine the modulus of elasticity within the linear portion. So this one here is the linear portion. I can determine the slope of that line. So for example, I can take this portion to determine the slope. Of course, it's going to be the rise over the run, but it should be only within the linear portion. Also here, it's required to determine the yield stress using the offset method and the yield stress using the extension method. We explained this. And also it's required to determine the secant modulus at a stress of 180 megapascal. So we need to locate this value, and then upon that you are going to determine the secant modulus. Go back to the definition of the secant modulus to understand what does it mean. Similarly, you are going to determine the tangent modulus at a stress of 180 megapascal. Also, it's required to determine the modulus of elasticity. We say that the modulus of elasticity is the energy required for the material to yield. So after you to determine, for example, you are going to use the offset method. Let's say this point here is the yield point. Then you are going to draw a line like that, and you need to determine the energy within this region. Okay, and regarding the toughness, you are going to draw a line here at the fracture point, and then you are going to determine the energy under the curve. Okay, so try to solve this problem here because you are going to solve this in the homework. Also, we have the failure and the safety. The failure occurs when a member or a structure ceases to perform the function for which it was designed. So if I'm going to have a structure, let's say beam or a column, we design that structure for a certain purpose. If that structure stopped to serve that purpose, that means failure took place. We have many ways for the material to fail. We have the fracture or the break. So like that, I have fracture here. The material originally was like that. Because of the loading, fracture took place. So in that case, I'm going to say that the material has failed. Also, we have the fatigue. Sometimes the material, because of the loading and unloading and the stress and the strain, tension, compression, the material is going to get tired. So through the time, the material is going to fail. And also we have the general yielding. Say that the yielding that we have large strain compared with the stress. Also we are going to consider that the material has failed. We have the buckling. The buckling means that I have the dimension of the length compared to the width is very high. Okay, so we have thin member here. So that thin member compared with that thick member, this one is going to fill through curvature like that. So when I apply the load, even though the material can sustain that load in terms of stresses, but here I'm going to have curvature. We call this buckling. So in thin members, we are going to see this type of failure. Also, we have excessive deformation. For example, this beam here, we have excessive deformation. So in this case, we are going to say that the material has failed. So we have many ways to claim that the material has failed. So in order to avoid the failure, the structure are designed to carry loads greater than anticipated. So let's say that I'm going to design that beam in order to take, let's say that stresses of 40 megapascal. So in order to be at the safe side, I need to, for example, design the material to take 50 megapascal. So I need to put additional safety. We call this process, we call that I'm going to provide factor of safety. So the factor of safety is defined as the ratio of the stress at failure to the allowable stress for design. So I'm not going to design according to the stress at failure. I'm going to design according to the allowable stress. And the factor of safety is going to be the failure stress over the allowable stress. And the factor of safety is going to be more than 1 to make sure that the structure has a capacity for the anticipated load. So how to determine the value of the factor of safety? So that is going to depend on many properties. The first one is the cost of the material. Sometimes we are going to deal with expensive materials. So in that case, if I'm going to increase the value of factor of safety, the cost of the material is going to increase. So it's better to minimize the factor of safety. If the material have variabilities, also I need to increase the factor of safety. If the of course, in the process of determining the loads, if your work is not accurate, I need to increase the factor of safety. And if I'm anticipating that I'm going to have possible misuse, I need to increase the factor of safety. And also, in terms of accuracy in measuring material response, I need to increase the factor of safety. So if I'm not sure about something, it's better to increase the factor of safety. So depends on all these factors. I need whether to get large factor of safety or a small factor of safety. In all the cases, the factor of safety, of course, should be more than 1. Also, we have the non-mechanical properties. The non-mechanical properties is all the properties other than the load response. We talk about the load response of the material. We call that the mechanical properties. Any other properties than those one is the non-mechanical property. Okay, and the most important non-mechanical properties, we have the density, we have the thermal expansion, and we have the surface characteristics. Regarding the density, you are familiar with the density. The density of the material is the mass over the volume, and also we have the unit weight, which is the weight per volume, and we have the specific gravity, which is the density of the material compared to the density of the water. Regarding the thermal expansion, we have that if you have material, if the temperature increase, that means we are going to have expansion. If the temperature decreased, that means we have to get contraction. So we know that all the material expand and contract with temperature. And we have the linear coefficient of thermal expansion. All the material, it has linear coefficient of thermal expansion, through which I can determine the change in the length, delta L. So in the strength of material, we use this formula here. We are going to say that the change of the length because of the temperature is going to be alpha L times the change in the temperature. So through that equation, we will be able to determine the expansion or the contraction because of the change in temperature. We already solved a lot of problems in strength of material regarding this. So for example here, when the structure is restrained from straining. So if I'm going to have structure and it's fixed in this direction and it's fixed in that direction. And then if the temperature is going to change. So if the material is going, if the temperature is going to change, so either to have expansion or contraction. So that length either it's going to be increase or decrease. And because it's fixed here and it's fixed there, that means the stress is going to develop inside the material. So normally, since concrete pavement, for example, are restrained from movement, they may crack in the winter due to drop in temperature. So if I'm going to have, let's say this one is a pavement and it's restrained from this direction and in that direction. So in winter, the temperature is going to drop. That means the material here is going to contract, is going to go this way. But because it's restrained here, that means tension is going to be applied for that material, so that is going to be in its original place. So if I'm going to apply tension, that means a crack may appear here. In the contrary, in the summer, the material is going to, the length of the material is going to increase. And in order to keep it within this region, I need to apply compression. So that is why sometimes you may find blow up in the summer due to the increase of the temperature. In order to solve this problem, joints is going to be provided in building bridges, concrete pavement, so that to accommodate the thermal effect. So it's very important to provide joints in order to avoid problems like that. Also, we have the production and the construction. It's very important aspect in order to select the material. I'm going to stop here since the time is over. Next time we are going to pick up from this point. Do you have any questions